So after learning how to figure out how many protons an element has based on its placement on the periodic table of the elements, we're going to determine how we can look at the data that we get from a mass spectrometer and figure out how to calculate this. On the AP exam, these particular graphs that I'm going to show you next are going to be what you're usually looking at. So how does a mass spectrometer work? So you take a sample. If you have a sample, remember I told you if you have 1 mole of atoms, it's 6.022 times 10 to the 23rd atoms, which is just an astronomically huge amount of atoms. So not all of the atoms of a particular element are going to be identical. Most of the elements on the periodic table of the elements have what we call isotopes. So one of the common applications is using the isotopes of carbon in order to what's called carbon date or radioactively date a substance. So carbon has a half-life of about 5,700 years, good for about 10 half-lives. So we don't use radiocarbon dating to figure out how old dinosaur bones are, because carbon has too short of a half-life. You would have to use an item with a longer half-life. But carbon would be good, let's say, if you were to find a piece of pottery in the desert and you wanted to know how old it was, you would use radiocarbon dating. And the way radiocarbon dating works is that you and I standing here while we're alive are ingesting heavy carbon, breathing in heavy carbon in the form of carbon dioxide in the atmosphere, ingesting it in the fact that plants that we eat uptake heavy carbon, which is carbon-14. And then once we die, we stop ingesting or breathing that heavy carbon, and it starts to radioactively decay back to our normal carbon, which is carbon-12. So that's one of the applications of isotopic abundance. So how does this work? We take a huge sample and then we inject it into what's called a mass spectrometer. And this mass spectrometer has an electron beam. That electron beam turns the atoms into positively charged ions, which are called cations. How that happens is how an atom becomes a cation is that it loses electrons. So this particular substance will knock electrons off of the atom, and then as it goes through the magnet, the positively charged cations are deflected by the magnet. Remember, magnets also have positive sides and negative sides. So what do you think? Is a cation going to be attracted to the positive side or the negative side? What do we know about charges? Do like charges attract or opposite charges attract? Opposite charges attract. So the negative part of the magnet is going to attract them, and then they will get knocked off course. And just like if you think of an object you're trying to push, picture yourself trying to push a very light ball. You give it a little shove and it goes very far. Picture yourself trying to push a very heavy ball, like made of iron. It takes a lot more effort to push it. So the smaller the isotope is, the more it will be deflected, meaning the more massive isotope is only going to be deflected a little bit. Let's look at what the graph is going to look like. So let's see if we can determine what element this is. You can see that the three things, everybody's following along with the notes now, the three things that this will tell us is the atomic mass of a particular isotope. It'll tell us which isotopes exist in the sample that we've injected in there. And it'll tell us the relative abundance, which is indicated by the signal intensity. So you have a computer program that analyzes the difference in the height of the signal intensity. So you can see that down here we'll find the atomic mass. This particular isotope has atomic mass of 35, and its intensity is 75.77%. So we're going to take 35 AMUs. Remember, sometimes AMUs is abbreviated U. And we'll multiply it by the signal intensity. Remember, the first thing we do is move the decimal point over twice, and that changes the percent back to a decimal. So 0.7577. Then we'll add it to the other isotope in this sample. The other isotope has a mass of 37 and an intensity or relative abundance of 24.23%. Like such. So before we add these up, let's remind ourselves what this means. This atomic mass here, the numbers 35 and 37 are the number of protons plus the number of neutrons. Now, when I'm doing these problems, I'm going to carry around all the digits that I get off of the calculator, whether I need them or not. I don't want to round until the very last step. When you're doing calculations, and that's the great thing about calculators, is they will carry all these digits for you. But when you're doing calculations, you do not want to round until the very last step. So I'll take 26.5195 plus 8.9651, and when I add it together, my calculator tells me 35.4846. Remember, we decided that we're just going to be okay with 2 past the decimal in this class. So my sample mass, average atomic mass, is going to be 35.48 AMUs. That's the average mass. Now I can go to my periodic table of the elements, and I can find out which element this is most likely to be. And I see that chlorine has a mass of 35.45. So the fact that it's not exactly 35.45 means that we're in just a little bit different of a region. So we're going to say that this element is chlorine. That means that chlorine 35 has 17 protons and 18 neutrons. Then we would say 17 electrons also for our initial sample. Then we'll say chlorine 37, still chlorine, so it has 17 protons, 20 neutrons, and in the original sample, 17 electrons. Does everybody see where those numbers come from? Okay, that's the example from your packet that I just handed out of notes. What I want you to do now is to practice a few of these yourselves. I want to come back at the end and do one more together to make sure we're good. The problem states rhenium is one of the rarest elements on the Earth. Alloys containing rhenium are used for oven filaments and X-ray machine. The average atomic mass of naturally occurring rhenium is 186.21 AMU. There are 2 common isotopes of naturally occurring rhenium. Using the information given below, calculate the percent abundance of naturally occurring rhenium. Now notice that the mass of rhenium-185 is given to you as 184.95. Not exactly 185, but the reasons for that are beyond the scope of this class, certainly. It's complicated stuff. So we're just going to not really stress about that. And we're going to say we have rhenium-185 with a mass of 184.95 AMUs, or U, which is abbreviation. Then we have rhenium-187 that has a mass of 186.96. They also gave us the average atomic mass, which comes from the periodic table of the elements, of 186.21. Now this time they didn't give us the abundances and we have to calculate them. So this can be a little trickier, but we can still do this. We know if they gave us the percents, how much would the percents add up to? They would add up to 100. But we're using percents as decimals. So if the percents add up to 100, how much do the decimals add up to? 1. So what we know is we don't know what rhenium-185's abundance is, and we don't know what rhenium-187's abundance is. So let's call one X and one Y like we would do in math class. And we are looking for abundances, so we know that X plus Y is going to equal 1. Abundances as a decimal add up to 1. Abundances as a percent would add up to 100. So we know that X plus Y equals 1. We don't want 2 variables though, do we? That's going to be complicated. So let's solve for Y. So carefully watch this because this is where the mistakes are made. If I rearrange this equation, I'm going to say Y is equal to 1 minus X. So the abundance of rhenium-185 we're going to list as X. And the abundance of rhenium-187 we're going to list as 1 minus X. I said be careful because the mistake I see made all the time is that people want to call it X minus 1. For some reason, we want that X to be first. But in this case, it is not first. So now let's calculate like we always do. Remember, we take the exact mass, 184.95, and we multiply it by the relative abundance as a decimal, which would be X. Then we add the other isotope, which is 186.96, and we'll multiply it by 1 minus X. And all of that's going to equal the average atomic mass, which is 186.21. Does everybody see where I got that equation from? All right, now I'm going to do the same algebra as you've learned in algebra class. This can be challenging to take what you learned in algebra class and transfer it to science class, but this is what we need to get used to doing. So I'm just going to expand this particular part of the equation out. So 184.95x plus 186.96 times 1 minus 186.96. So now I'm going to gather my like terms together. Let's put our x terms on one side and our not x terms on the other side. So 184.95x minus 186.96x gives me minus 2.01x. 186.21 minus 186.96 gives me minus 0.75. In order to get the value of x, I'm going to divide negative 0.75 by negative 2.01, and I get 0.373134 in my calculator. What that means is my percent, remember the percent of rhenium-185 is x. My percent of rhenium-185. What's the easiest way to figure out what the percent of rhenium-187 is? So I can plug in x, which is 0.373134. So 1 minus 0.37314. The other thing I can do is take 100 minus 37.31, and I get 62.69%. So that's as tricky as these problems get. And it's a good math skill to practice.